So in a previous demo, we were able to use a single pixel in order to confuse an image classification model to classify a picture that appears at face value to be a cat, but to get it misclassified as a dog. And if we run that particular demo and example again, we can take a look at to see what our result here is. So if we take a look at the cat picture, which is the normal unaltered picture, you can see that the cat is the predicted class with a confidence score of 100%. The dog is predicted to be a dog with a confidence score of 99.95%. Now the cat picture with the single bad pixel where we've modified and done an adversarial attack using a 1 pixel attack against the model that was trained to get this cat picture classified as a dog. And again, if we use an observability tool like Captum, this is what the positive attribution looks like for the correct or unaltered cat picture. You can see that on the right hand side, all the attributes that contributed to the positive identification for this being classified as a cat. And if we look at the altered or the bad cat picture, we can see that we placed this single pixel right here in the upper left hand corner of the original image. And when we use Captum in order to observe how the model classified this as a dog, it was due to this single pixel right here in the corner, upper left hand corner. So this is how we can use a single pixel to modify our data set in order to misclassify on purpose through an adversarial attack to misclassify images. So you might ask yourself, how can we defend against this particular attack? Well, this can be done on multiple levels. The best way is to make sure that our original data set has not been ever tampered with. There are many tools out there. NetApp provides many capabilities in order to preserve and make sure that the data sets that you're using in your machine learning and AI training are not being manipulated in any such way. Now, should you be in a situation where you aren't observing AI and ML best practices for AI and ML governance and observability, where your data sets are idempotent so that they can't be tampered with. So there are many methods available to protect yourself against adversarial attacks, against image classifications, and image problems in general. The first method, which is fairly easy to do, is to use color bit depth reduction. Individual pixels don't dramatically affect the overall classification of images since the pixels themselves become a little bit more coarse. The one that's really easy to use, and the one we're going to apply in this particular demo, to take the image and apply spatial smoothing to that particular image. It effectively blurs the image so that individual pixels will be averaged out or smoothed out over surrounding pixels. So as you can see in the code here, we've taken the bad cat picture, we have done median filtering or smoothing or blurring the image, which you can see indicated by the size 3 here. Then we have the smooth cat picture, and we can run that through the machine learning model for inference. Let's go ahead and give that a try. So you can see if we take the smooth or blurred picture, which makes that individual pixel or 1 pixel attack less effective, we get the correct classification of cat using our image classification with a confidence score of 89.5%. So if we use Captum to take a look at what parts of the image positively attributed to this classification, you can see that the other aspects of the cat now come through because this pixel in the upper left-hand corner now becomes far less prominent because of the smoothing or the blurring aspects of the transformation on the image, thus combating the adversarial attack and yielding it the correct classification of a cat. Something to notice though is that the confidence score is slightly lower at 98.5% compared to the near 100% confidence score on the unaltered cat image. Some interesting things to think about on which method you pick in order to combat this type of adversarial attack. I hope you enjoyed that demo.